Hello everyone, I am back again for another video. Today we're going to be talking about the rate constant K. So just as a explanation, in our rate law, rate equals K times the concentration of some reactant raised to the nth power times another reactant, blah, blah, blah. So today's whole focus is going to be on K. There's not a ton to say about K, but there are a couple of things that are kind of important, especially when we talk about some special instances like half-life of first-order rate reactions, things like that. All right, so I'm going to step off to the side, pause the video, copy down the notes. I'm going to come on back and let's talk about it. Okie dokie, hopefully you guys copied down all the notes, had plenty of time. A couple of things, the rate constant K changes a lot based on the reaction. And that's just because of the nature of reactions. For example, some reactions are very, very slow, like graphite actually, or diamonds actually turn into graphite over millions of years. So if you have a diamond sitting in the earth, sitting in the rock, over millions and millions and millions of years, hundreds of millions of years, slowly that composition of graphite will turn in, or that composition of diamonds will turn into graphite. And it takes a long, long, long time. There's no worry about someone's diamond ring turning into graphite overnight or anything like that. It takes a long, long time. Well, since it's such a slow reaction, you would expect a very small K value to correct for that, okay? Because our rate is so small. Whereas gasoline burning is a very quick reaction. Gasoline burns very quickly, or most combustion reactions are very fast. And that means that that's going to have a very high K value because we're going to have a very high rate. So our K values are very different. You can have a K value times 10 to the negative fourth and a K value times 10 to the negative fourth. Times 10 to the fourth and 10 to the negative fourth, yeah. All right, so our K values can vary quite a bit within different reactions. The important thing to note is that within one reaction, so let's say we're talking about that diamond slowly turning into graphite, it's going to have a set K value. The one thing that will change that K value, or the one thing that changes that K value most, I should say, is temperature. Reactions are very temperature dependent. All right, so for example, fire is a great example. Gasoline burns at a high temperature. So when the temperature of the gasoline gets high enough, usually due to a match or something like that, when the temperature, or the engine or whatever, I guess I shouldn't assume arson here, when the temperature of the gasoline gets high enough, the reaction starts and the reaction proceeds very, very quickly. Well, if my reaction is below that threshold temperature, my K value, my rate is very slow because the gasoline doesn't burn. It doesn't have the energy to kickstart. So it's very, very slow reaction, you could say. Or let's say it's the difference between, let's say like a smoldering fire versus a nice bonfire. A nice bonfire is a very quick reaction, burns through the logs and they fuel very quickly because it's very hot. Whereas a smoldering fire tends to be cooler, and so it's a slower reaction. Same reaction, same combustion of a log burning, but one is slower and one's faster, and it's usually due to temperature. And we're going to get into why temperature affects it in the next couple of videos, but right now we're just going to leave it at temperature does affect our K value quite a bit. A special instance, and we're going to have a whole video on the half-life and how to solve half-life equations, but the half-life of a first-order rate reaction. Now, you don't have to have this memorized. It'll be given to you on your equation sheet, but it's actually a weird half-life. It's saying that half-life, T1 half, so time, half-time, right, half-life, half-time, equals the ln of 2. All right, so that's just the ln of 2. It's like 0.697 something, maybe. Just the ln of 2 over your K value. Okay, so the half-life actually is just the ln of 2 over your K value. And the reason that's so interesting, that's the only time your initial concentration doesn't affect it. So if you think about it, a lot of times, the more you have, the faster it'll start decomposing, or faster it'll start breaking down, the half-life. We think about, the breaking down of it. So, but whereas this, it doesn't really matter. A great example of this would be like nuclear decay, right? If you have a little bit of nuclear waste or a lot of nuclear waste, the half-life is still the same. The half-life is whatever, 1,000 years, 5,000 years, a million years, whatever it is. Or carbon-14, popular dating, radiometric dating. Doesn't matter how much carbon-14 is in the sample, the half-life is still always, I think 4,000 years. So On a first order rate reaction, the concentration doesn't affect it. And that's really important because then scientists start talking about the rate of something in terms of half-lives and not in terms of the rate reaction, right? We can't say, oh, the half-life of compound X is 5,000 years if it's not a first order rate reaction. All of my other rate reactions, the concentration affects it. So we can't talk about half-life of those because there's a concentration that affects the half-life, right? If I have 10 gallons of compound X, maybe the half-life is 5 years, but if I have 2 gallons, maybe the half-life's only like 1 year. So, but on a first-order rate reaction, we can because it doesn't matter about concentration. My half-life is inversely proportional to the rate. So the slower the reaction, the lower the reaction, the smaller the K value, the bigger my half-life. So small reactions have very long half-lives. Quick reactions have very short half-lives. Okay, and the classic example of this would be like radiometric dating or radioactive decay, things like that. All right, so this was a quick little primer of rate constants and half-lives. Please remember that temperature affects rate constants most of all, and that my rate constant can vary widely based off of the fact that different reactions have different speeds or rates. And then last but not least, on a first order rate reaction, half-life is independent of concentration. So half-life tells us about K values. It's inversely proportional to K values. And we can also talk about half-lives between different amounts because it doesn't matter how much there is. Now there's going to be a whole nother video just on how to solve half-life equations. So if you're a little unsure about half-lives, don't worry, it's a load of fun. All right, I will see you in class.